Okay, any questions from the sheet metal tutorial or the shop videos from last night? Reminder, make sure that you upload homework 2 by 10 o'clock. So that's your SolidWorks final project declaration in either Word or PDF so I can read it. That goes into the homework 2 folder on Dropbox. Thank you. And then let me explain let's assign and explain the SolidWorks final project with everybody here. So tonight you're going to have, or this weekend you're going to have homework 8, which is going to be to create a solid model and drawings, or a drawing, for this electronics box. And then your quiz 4 is to actually build this box. Now, we need these boxes. We're going to use this in lab. So we want you to do the best job you can. So Professor Hodgkinson here is going to show you the machines and how to work sheet metal today. And I'm going to show you some more advanced stuff on sheet metal beyond the tutorial that you took. So the assignments are 2. It's homework 8 to build a solid model of this, and which is a solid part. It'll be first name underscore last name .sldprt, uploaded on Monday by 10 to D2L under homework 8. And then a drawing file that's the flattened drawing, which you will then use to tape onto your aluminum. He'll show you that, and cut it out and bend up the box. And you're actually going to make this. But I want you to be very cognizant of what you're doing. Take it slow, measure twice, cut once, because we need these to be good. Hopefully out of, how many groups did I say we were going to do? 17. It was 4, 3, 5s.
6 groups.
2.
5 groups of 3 and 1 group of 2.
Right, five groups of 3 and 1 of 2. Okay, so out of the 6 that you're going to make, it'd be really nice to have all of them, really, but how about them?
6 would be great.
So we'd really like to get 6 of these that are useful for aerospace engineering labs. You are going to CAD model and build this entire thing for your SolidCAM final project as part of a group. And I don't care how you guys split that division of labor up, as long as it's relatively fair. And if there's not a fair division of labor, let me know and I'll grade accordingly. But this one part of it is going to be homework 8, the modeling, and then quiz 4, the building. And that will count also, so it's a double dip, it'll count also as your part of your SolidCAM final project. We will hand you material probably today. We'll hand out material for this today. We're going to give you a few hints. So I'm going to give you how we made the base flange bends, and we're going to give you the material properties that we use and the bending radii for our machines so that you can complete this. And I think we'll go over some of that today in class. But that's about it. All the rest of the dimensions you need to measure off of this part carefully and update your models using those. So you'll have to take this apart, which is okay. Just put it back together when you're done. The dimensions you're going to have to be concerned about are hole sizes, hole locations, both for the grommet access holes for the USB cord and a finger to push the start button, and for some wire harnessing, and the mounting holes. There's 4 of them that mount it to this base plate. Okay? Because it mounts to this base plate, you're also, in order to properly finish this part, you're going to need to measure these base plate holes and add them into your model. So this base plate is just part of the larger SolidCAM final project, but in order to complete this box, which you need to do by, at least the models need to be done by Monday, and I believe the box itself needs to be done by Wednesday. You're going to have to model at least the holes on this base plate. So you might as well take measurements on this base plate. So you're probably going to have to come in and take measurements off these things this afternoon in order to get this done. Okay? Won't take a ton. You can take your measurements, write them down on paper, and then you can take them home and finish your model. But you're probably going to have to do that this afternoon. Any questions on that? Remember, the groups of 3 will have an extra component to build and model. And I believe it's going to be this, right?
Yes.
Do we just want to do this? All right, so it'll be the arm.
It won't be exactly like that. We'll give you the actual solid part file, and then you'll just make it from there.
Okay, so
we also need to give them the motor, because we have a specified motor, and then the specified gears, and then the potentiometer.
well, they're here. We could take them apart here,
Correct.
but if you want to give them extra pieces. So we're going to put this model out on the main workbench in the shop, and then you can take it apart and take dimensions. But you should probably put it at least a little bit back together for the next person.
So are these homeworks and quizzes done with your group you're going to use, or that you're going to do with the solid cam project?
No, this is individual. But you can use the model that you created and just use one copy of that, the best, cleanest one, maybe the one that gets the full points, and use it for your group in your final model. And then the base plate can be one person working on the base plate. Okay? Other questions about this? So we'll be leaving this out from here on out so that you can take measurements as you go. We're going to engrave these. ASEN 2003. Clearly this is unit 1. You all need to pick a different unit number, starting with 2. So some of you will be 2, 3, 4, 5, and on. Okay? So I could manage that process, or maybe you guys could just do it between yourselves. Figure out which number you are. All right? Any other questions there? What do we want to do about extra holes? There's a few extra holes we don't use anymore. Just have them do it.
Let's do it. So you'll make the base plate basically as it is. We may not use those holes, but it's better to have those holes now, and then we can use them in the future.
So you're going to replicate this model as it stands. What about this double stack thing here?
No, so the double stack, the arm, and then the cylinder above it will become the unit that will give you for the rigid arm assembly. So for those groups that are making the upper arm, you'll get that as 1/4 inch plate.
Okay, so the groups of 3 will be making this arm and a second disc?
It will be one, it'll be out of
Oh, it'll be out of one
plate.
piece. Okay.
Right.
So the groups of 2, you're going to replicate this. This top piece is all you make. There's a second disc up here that's stacked on top of this first disc, and this arm. The groups of 3 will be making that as one component. Instead of 2 pieces, it'll now be 1 piece. See what I mean? This arm and this top disc will be 1 piece instead of it's 2 right now, screwed together. We will now be changing that and making it 1. We'll get that to you later for the groups of 3. Groups of 2, don't worry about it. This whole arm and this top disc are gone. You're not dealing with it. Questions? I think we could split then, although I was hoping to send this around. Everybody that's leaving, go sign this first. Who do you want?
Who wants to get dirty first, A or B? A.
There it is. A's leaving. See ya.
Do you want to keep the Quanzer in here, or can I take it?
You can take it. We're going to leave it in the shop from now. I just wanted to show them what they're replicating. Should we just have them do the solid part, not the drawings? Let's just have them do the part for that.
The entire thing?
Okay. So, for your solid cam final project, you're physically building that thing and you're turning in the solid part files, but you don't have to make drawing files for it. I'll reiterate that later. Okay, so just as a reminder, on homework 8, the assignment is here, and there's a rubric associated with it, so that's all there. So you should be, if you have any questions, you can look there. You can always email me if you need to. Okay. Let's go into more depth with sheet metal, and related to that, I'm going to show you some manufacturing type stuff that goes along with that. So, I want to show you this from last year. Last year, we made a bunch of electronics boxes out of sheet metal. But they were different ones. They were just kind of general ones for general use. And we've been using them. Senior projects have been using them, and grad projects. So those are pretty cool. But I wanted to just show you this. You'll be making a different one this year because we need it for that controls lab. But this one is very good to show you in SolidWorks because not only is it a sheet metal part, but we can talk about two concepts. One is building parts off of other parts within assemblies, and a second concept is the idea of an adaptive part. So, for example, this box was spec'd out by Trudy, our electronics staff person, to be a 5-inch by 7-inch by 3-inch box. But she also spec'd out other sizes of boxes that she liked. So rather than make one 5 by 7 by 3 box, and then when she comes up with a new set of 3 dimensions, rather than having to model this whole thing over again, it would be cool to just go into one part, change the 3 dimensions, and boom, have everything adapt, all the parts, all the screws, all the fasteners adapt, and make a solid model just like that within seconds. But you have to design and build your CAD model in order to do that. That's called design intent again. And it's a little tricky to do, but I'm going to show you how to do that here. But this is the final product here. Let's see. So it was comprised of a top part and then a inside part, and then we have these little fasteners. These are called captive fasteners. They're one style of a captive fastener. It's called a Pem nut. This is a Pem style fastener, and what it does is it has this little knurled area on it, which kind of compresses into the aluminum, and then embedded within it are these threads. These threads here, in this case for a 440 screw. So quick test, Alex, what does 440 mean? Explain what the 4 and the 40 is.
The 40 is the number of threads per inch.
Correct, which is also called the, help them out, pitch. Pitch. Threads per inch means pitch. Okay, and the 4? It's the gauge size, but what dimension of the screw does the gauge size? Right. What do we call that on a circle? The diameter. Thank you. All right, and then we have screws here from our toolbox. So these PEMs, the way they work is you sort of barely crush them into the aluminum so they kind of stick, but they really get their ultimate strength when you actually put the box together. That screw pulls those threads into the box, so then it's captive, it can't go anywhere. So those Pem nuts are very useful for nuts on sheet metal because it would be almost impossible to put this box on top. Imagine trying to put the box on top and hold the nut on the inside. You just can't do it. So you have to have this little Pem nut to hold it in there. I'm going to show you some interesting, things related to that, but basically I wanted to show you this box because we're going to be doing something very similar. It's different for your assignment, for your homework. You're making a completely different box, and you're not going to be making adaptive parts, but I want to show you adaptive parts and show you building parts within assemblies because it's very powerful stuff to know. Okay, and so let me show you an example of what I mean by adaptive, because I believe that these parts as I made them are not adaptive. So if I go into my base flange and edit my sketch, not on this component, I want it on the other one. Or do I? Yeah, so here I did 7 by 3. What if Trudy comes to me and says, I don't want 7 by 3, I want 10 by 2. And then exit the sketch. Let me exit the part. See what happens? So it did change that component, but this component didn't change to match it. And the screw holes now do not line up. Can you see? Can you see that little orange screw hole there? Doesn't line up with that one now. Okay, so I made 2 parts and I made an assembly, but if I change any of the dimensions, it doesn't all change. You can force SolidWorks to make it all change and be perfect, just like that. So we want to do that. So part of this lecture is going to be about that. It's a little tricky, so you're going to have to pay attention, and of course I've got it videotaped so you can go back and look at it. Before we go into that, I want to show you a couple of interesting items related to this. So I'm going to open those same ones, the outside and the inside part, but just the parts. I'm not going to make the assemblies. And then I'm going to start a fresh assembly. And I'll insert those parts. Actually, I'm just going to insert this one for now. What I really wanted to show you was the screws and the Pem Nuts. So we know where to get the screws. Let's go into that again. Design Library, Toolbox. And it's already been added in for me, so I can just go to American Inch. And I'm going to go to Bolts and Screws. And I'm going to go to Machine Screws. No, I don't like that. I'm going to go back to Bolts and Screws and go to Countersunk Head. And Countersunk Bolt. Although I think this is going to be too big. We may need to be in the miniature sizes, but let's take a look. So I drop one in and I look at my sizes. They start with 1/4 20. So that's not what I want. I wanted 4/40s. So that's kind of common terminology. There isn't an accepted standard really, or an agreed upon standard on when you refer to a fastener as a screw and when you refer to it as a bolt. Bolt in general means big, heavy duty. So you're not going to get real small stuff with bolt, but people will say screws sometimes, so you have to be careful. I'm going to go to Machine Screws Countersunk. How about that? There we go. This is what I wanted. Now notice there's a couple of different kinds here, and there's more than just 2. One says 100 and one says 82. That refers to the angle of the countersink on a flathead screw. 100-degree screws it's a larger angle, and if you have a larger angle, I'll draw this on the board, as opposed to this angle, this dimension of this screw, this height, is smaller. So you can fit that in thinner pieces of sheet metal, as opposed to this one. However, the 82 is really pretty much the standard for just about every screw you're going to find. Just about everyone's an 82. So these hundreds are kind of special order. Now they carry in places, McGuckins carry some, and they're online, but just be aware that this is the more common fastener. Also, just so that you know, flathead screws, the length is measured from the top of the head. So if this is a 1/2 inch a 440 machine screw, that really would be about a 1/2 inch, nominally a 1/2 inch. Nominally means about. Whereas a socket head cap screw like that, the 1/2 inch refers to this dimension, just from the underside of the head to the end of the bolt. So be careful when you see 1/2 inch bolt. It means different things in different places. All right, questions there? So this was, I can't remember what these countersinks were, and it doesn't even have a countersink, but I do know that these are thin. So why don't we add in a 100-degree screw just to make it thin. So I'm going to drop that in, and I wanted a 440. Oops. I don't know if that's what I wanted, so I'm going to delete it because I jumped the gun on the options. So 100-degree screw. Come on. Size 440. I don't know about the length. I'm going to make it pretty, I wanted it to be pretty short. Let's go with their smallest one. Let's see if that works. And then we know it's a 100-degree screw, so that's good. And we'd have to put in 6 of them. But we may be able to mirror these. So I'm going to put in 3 for now, and we'll see what we can do. Alright, so I've got screws, and I could mate them when I get to it. But for right now, the next thing I need is those cool little Pem Nuts. Alright, that go on the back here. Now I believe they've got Pem Nuts in our ANSI inch folder. Let's take in our toolbox. Let's see if they do. Go down to the bottom. They have Pem in inch and Pem in metric. Let's go nuts. Nuts non-locking. I've never tried this before, so we're going to take a look. And there they are. They do have them. So they have aluminum ones, self-clinching ones, and SS is stainless steel, S is steel, etc. Let's try this self-clinching and drop that in. There's one there, and you can select it to be a 440 thread. This particular one's a carbon steel. Let's put a stainless steel in just for fun. Okay. It shows you a minimum sheet thickness of 0.03. I believe this is 0.05, so we're good. And we've got one there. All right. So our SolidWorks toolbox actually had this. You can look at this nut. And that way you don't have to model it. Now I'm going to show you something else cool. A lot of these industrial supply websites are starting to get, they're starting to cater more towards engineers than just hobbyists. So they're actually dropping in CAD models of a lot of the stuff that you can buy, components you can buy. So I want to show you that. Let's go to McMaster-Carr. Told you about that. McMaster.com. And let's look at Pem style nuts. Okay, and Pem is just a brand name. It's kind of like Kleenex. You know, Kleenex is a brand name for tissues, but they were been around so long and been the biggest manufacturer that people just think Kleenex is actually the tissue, right? It's the same thing here. These things are called they're called captive fasteners, and there's different styles of captive fasteners, but Pem kind of came up with the first one, so we kind of just recognize them as Pem. See how they're called captive nuts? That's a more generic term. But let's take a look at this. We've got tin plated steel ones, that's fine, in 440, and you can click the part number, and then if you look here, not all the time, but a lot of times on this website, under product detail, they'll have this little CAD symbol. You can click that, and it shows you a CAD drawing. Notice they have their own little title block, so somebody at McMaster Carr must have taken my class and made their own little title block. That'd be so cool if it was somebody. And then they've got dimensions. Now you can just look at the dimensions for when you're trying to select, you know, parameters in your solid model, or if you want, you can download this thing, and they have it in a bunch of different file types. They actually have SolidWorks, so I'm going to go ahead and download that file, and then I'm going to open it, and there it is. So now I can save, and they've got this part. Not only did they give us the part, but they gave us the entire SolidWorks model. We can even go in and modify it. Sometimes they'll give you a SolidWorks model and they won't enable any of the features. But in this case they did. So we could go in and modify things as we see fit. But notice they named it their part number. They want you to drop this in and have a McMaster part number so that you go and buy from them. However, that becomes good for you later when we start talking about drawing trees. If you've got McMaster part numbers in your drawing trees, you can very easily take those part numbers, compile them, and then send it to a purchasing person within your group and have them buy the stuff from McMaster. But there it is. So we could go to our assembly and we can say insert component existing part and get this McMaster number and drop it in. Now notice this looks a little different from this. They should be the same nut, but maybe they're not. Or the CAD modeler that modeled each of these went about it a different way and just got a little bit different result. So it's either a little bit different nut or the CAD modeler got it a little different. You wouldn't be able to absolutely know until you bought these things, got them in, and validated the solid models by measuring them with calipers. Okay, but you could drop them into your model right now and it's probably going to be close enough. What we do know is that the 440 threads are going to be consistent across both pieces. Okay, questions there? That's a pretty cool little feature, and McMaster has a lot of these drawings. I mean, a lot of this stuff you'll find. Little hint for your SolidWorks project, if you go to, let me open up the instructor's TA's version of what you're going to build. Remember, your SolidWorks or SolidCam final project, your team is going to basically turn in all the files that will get me this. If I open up your assembly, I should pretty much get what you're about to see. I'm not going to have you do drawings for them. You have to do drawings for your SolidWorks final project, so I'm not going to make you do drawings for this one. But I do want the hardware, and I do want the parts files in the assembly file. So you're going to provide this to me. The groups of 2 will provide this exact kind of thing because it's got the one disc at the top. The groups of 3 will have that added arm. As soon as this opens, I'll show you, because many of these components I got from the McMaster website. I actually bought these components. We'll hand them to you. You don't have to make them, and you can drop them into your solid models, but you need to know where to find them. So that's why I showed you. So let's see if this thing will open up today.
Are we going to be just handed just the real model and just have to measure out all the pieces? Or?
That's correct. That's correct. So part of this exercise is seeing if you can reverse engineer or measure carefully and get all these things modeled in CAD and then machined in CAM and get them to all fit together. That's part of the exercise. If you can do this, you're pretty much ready for anything you're going to see in college. So, and you'll be the star on your group when you're in a projects group. You can say, I know how to do that. All right, so for example, I believe I bought, this is a little right in here. This is a potentiometer, and this is a shaft, and the little shaft on the potentiometer and the little shaft there needed to be coupled. So we used a shaft coupling that had set screws in it. And if you notice, there it is in my feature design tree. Here's the part number, 6412K110. So if I go here, 6412K110. There it is. Black oxide steel without keyway, set screw rigid shaft coupling. Product detail, 3D SolidWorks, there it is. So some of these things you don't have to model. It's already been done for you. It's going to be the more custom components. Now, there are things that aren't modeled. I believe the feet. I bought the feet from McMaster. But if you look at this, it's feet. I had to actually design it because they didn't have that part number, or they had that part number, but they didn't have a CAD model for it. They had a drawing, I believe. Let's take a look. Right here. So I ordered this component, and they had product detail. Well, look at that. They had it. I could have just downloaded it. What was I thinking? So be it. I could have gotten away with a little bit less modeling there. So there we are. Any questions there? It's a pretty cool thing.
We're going to know which parts we don't need modeled. Like, you're going to give us the bag of things we don't model beforehand, and we just have to guess which ones
So,
are.
I mean, we haven't fully discussed how we're going to present the assignment to you. We just let you know today. We're kind of going to probably going to give it to you a little bit piecemeal. But that's a good point. Yes, there are a whole bunch of components we bought and we're going to hand you. So we could probably just hand those over to you. I haven't decided how we're going to do that yet. The way you're going to be graded is you're going to turn in all the parts and we were going to put it together. And we're going to see how it functions and how it looks. And then we're going to grade you on that. So I don't know if we'll give you all the pieces, but maybe we should probably give you one of each. So of the 4 feet, maybe we give you one. Maybe we give you the shaft collar. I'm a little nervous that you're going to lose them, but I guess
Or you can just tell us which ones.
Sure. We'll probably put the bin out of stuff, and you can see what we have purchased already. The rest of it will be obvious because it'll be raw material.
Yeah.
So you'll have to definitely model that. Okay, that's a good question. Others? For example, these standoffs, we bought those. So there's a lot of stuff that's bought in here. I know it seems like a daunting task to build this, but it's all kind of pretty square stuff, pretty simple modeling task. It's more about the machining that I wanted you to do. But I also wanted you to practice measuring and get this right. Make sure that you are accurate and careful with your measurements and your modeling and your cutting so that you can get everything to go together. There's also a lot of stuff in here that you're going to learn. Bearing presses, alignments, that sort of thing. So it's good stuff. All right, back to our sheet metal. Before we finish with this, I just want to show you some mating on the fasteners. You probably already know this, but let's just practice just a little bit. We'd like to put this Pem on the inside of this, so we'll mate perhaps this face with this face, and that is the correct side, so I'm good there. And then if I wanted to put it on this hole, I would mate, say, this hole with that hole concentric, and we're popped in there. Okay, let's say that I went, let's go ahead and mate this one too. I won't do all three, but let's just mate this one too. Sometimes you can't grab this face, so I'll zoom in. Now I can grab that face, and we want him on that face. And then we want to mate this circle with that circle concentric. Okay, now I would have put in a third fastener, just going to be lazy and not do it. And I could have gone through and I could have mated 3 more fasteners over here. Or I could mirror those components because we have symmetry here, right? These 3 and these 3 are symmetric about an imaginary what that runs through the middle of this thing. Plane. So in order to mirror these components, I would have to drop in a reference plane, which will be created from 3 points. So we need to create those points. Now, so I'll go to Sketch, 3D Sketch, and I know I want 2 of those points to be the midpoint of this guy. And the reason I want the midpoint, I don't want to hard code a number. I want the midpoint because if this box dimensions ever change, it'll always be the midpoint. No matter how big or how small it is, we always want the fasteners to be mirrored across the midpoint of that plane. And that way it doesn't matter how we change the box. So we want a couple of those. Midpoint, where are you? Midpoint. Oh, maybe do I have to accept that other point? Yeah. Alright, midpoint. And then we need a third point somewhere for a plane. I wonder if we could probably can't make them collinear, but what you could do is put a point on this midpoint. And I know they're pretty close together, but won't that still create a plane? Alright, so I'm done with that. And then I want to insert reference geometry plane. First reference, we'll grab this little point. Then this guy. Hey. Okay, it's kind of trying to start to form a little plane. And then third reference, that guy. And there's our fully configured plane. Now it's kind of little looking, but if you can just use your imagination, that thing extends infinitely in all directions, so it doesn't really matter. So we'll accept that. And now I've got this plane. Now if I mirror these components through that plane, they should just show right up, right in there. So we select these two components. So these two. Then we want to mirror them. I forget where that is. So it's up in assembly, linear components, assembly, linear components, and then you do the what? I'm sorry, what? Yeah, I got you. I got you. I'm trying to show it to you slow. So assembly, linear components. If you do the, so it says linear here, but if you drop it down, you've got mirror components. So components to mirror, it already dropped in these two because I selected them, and then the mirror plane will be, I don't see it here, so how would I find it? Right here. This little ghosted out feature tree. Click that, and then you'll be able to find your plane. Accept, and now I've got mirrored components. Okay, so especially, I mean, it didn't really matter with three parts, but what if I had 100 of them? You probably want to start using linear components or mirrored components or something like that. The other nice thing about this is it doesn't matter how I change this box. These fasteners will always be mated to this plane, and these ones will always be mirrored in that plane, which is directly in the midpoints, so it's definitely going to go to the other side. So it's a completely adaptive part. I just change 1 or 2 dimensions, and it does what I wanted it to do. All right, questions there? All right, so, and then we talked about the other box. Not this guy. We talked about the other one where we wanted not only if we change the dimensions on this inner one, we want this outer one to adapt and grow or shrink such that it still fits on there, but we also want the holes to line up no matter what. So we're going to go into that. It's kind of a long, involved process, so we'll start it here. We will probably not finish it in this segment. It's break time. 9:50, about 5 minutes. Okay. All right, so like I said, 2 concepts that we're going to learn today is building parts off of other parts in assemblies, and adaptive parts, parts that grow or shrink or change based on changes you make to another part. Okay. Let's open Matt General Mail Test. All right, I'm calling this the mail side of the box. So imagine I made this part. I know this is the part I want. It's the inside part of the box, and I've got, you know, my little holes, and you should understand the base flange from your sheet metal tutorial. And then I have a cut extrude, which is the holes. So that's really all this part is. It's a base flange that's 8x3. So if I ever wanted to change the size of this box, all I have to do is go into this sketch and change these 2 dimensions. Now, what about the third dimension? So I've got the 8x3. Where does the third dimension come in? That's this one here. So these 2 dimensions come off of this base flange sketch. So I'd change them within the sketch. The third dimension comes from the feature itself. It was extruded out a certain distance. In this case, 8.5 inches. So if I wanted to change the third dimension, I'd have to change it here. But what we'd like to happen is if I change those 3 parameters on this part, the female part or the outside part adapts and all the holes line up every single time. And that way we can make an infinite amount of boxes by only changing 3 little parameters. It's really fast rather than building a whole new model every single time. So that's what we're going to do. So in order to do that, you have to do something called building the part off of this part within an assembly. And before I go to that, you're going to run into trouble. I'm going to open the sketch. You are going to run into trouble if you build parts off of assemblies and there isn't a common reference. So for example, look here. Notice that my base flange sketch for my 8x3 box is not anchored to the origin. So when I go to change this 8 inches, it may go one way or it may go the other. It's not anchored at the origin. So when my female box that's on top of it adapts with it, it may adapt the wrong way. So it's just a generally good rule of thumb that if you're going to build parts off of other parts, start with the base anchor part at a common reference like the origin or some sort of reference geometry point. So just in case, maybe I will change this and make it go to the origin. So I've got a fixed point that's keeping me there. Let's take that relation off. And let's add a relation that makes that guy and that guy coincident. And now I'm at the origin. Hopefully that doesn't screw anything up. Okay, so I started with a part anchored at the origin. And it's going to matter where I'm anchored at the origin. So notice that I built this part by sketching it here and extruding it this way. And that may become important when we go ahead and put the female part in there, because when it changes, when this dimension changes, it's going to change in this direction. So that female part has to also change in this direction. Okay. All right. If we wanted to build a part off an assembly, what we want to do is go, you're in this part file, go up to the top and hit Insert, Insert Component, New Part. Where's Component? Do we have to start an assembly? Oh, I did this wrong. I'm going to save this file. Oh, no, we don't. Now we can go to, I'm sorry, we can go to here, File, Make Assembly from Part. So we're going to make an assembly to ask for the template. And I'm going to start with this file. Come on. Okay, there's an assembly now. We're in an assembly. And I've got this part in here. And now I want to go to Insert Component. Instead of inserting a part I already built, I'm going to insert a brand new part that I'm going to make. So we go to New Part. All right. And if you look here, this is the trick. You may be confused. So you now have an assembly and you've got a part in this assembly, but if you start sketching on here, you will be modifying the assembly, not the part. Okay? You're working in this assembly. If you want to modify the new part that we're about to make, it's right here. Part 1 within Assembly 2. So if you want to work on this part, you need to right click and edit this part. That's tricky right there. Your first inclination, and I made this mistake too, is okay, I've got this part, I'm going to start drawing a new part right here, right in this window. It will not work because you are in the assembly right now. You are not in this part definition. That's a critical key here. So to get into this new part, you click it and then you need to hit Edit Part. You'll know that you're in good shape by seeing this little icon in the corner. What this means is, do you want to go back to the assembly? And the answer is no. We're working on this part. So you can see also here, this is turned blue. Now you know that you're editing, you're making this new part that has nothing, it's zero. There's nothing about it right now. But there it is. Okay, do you understand that part of it? So I'm a couple minutes over, sorry. Off to break with you. And then you guys will go to the shop by 10:20. Or no, I'm sorry. 10:05.